Welcome to Lecture 6 Part 3. This lecture is on the topic of nutrient management, concentrating on the macronutrient phosphorus. This subject, Agronomy 1, is part of 2 degrees, the Bachelor of Agricultural Science and Technologies, as well as the Equine Studies degree. Both of these degrees are offered at Melbourne Polytechnic, while the Bachelor of Agriculture and Technology is offered at Melbourne Polytechnic and in a partnership with La Trobe University. For more information on our courses, please visit our website at www.melbournepolytechnic.edu.au. My name is Dr. Nikki Cooley. As said in the previous slide, this lecture was Part 3. In Part 1, you will learn about the overall components of fertility, the chemistry of fertility, and general points about nutrients. In Part 2, we concentrate on the macronutrient nitrogen. This is Part 3, where we will concentrate on the macronutrient phosphorus. It is advisable that you watch at least Part 1 before continuing with this lecture. This lecture, we will structure it very similar to the lecture on nitrogen. That is, we will start on the chemistry of phosphorus. We will learn about phosphorus sources. We will learn about how plants use phosphorus, how you can test the soil for phosphorus, and how you can apply commercially phosphorus. Now we are going to talk about the macronutrient phosphorus. On the slide you see 3 images. One image is of red phosphorus as a powder. The middle image is of many phosphorus molecules. And the left-hand side is a Wikipedia image showing the elemental state of phosphorus. It has an atomic number of 15. I'd like you to follow the link on the screen and watch the video on phosphate and potassium. This video shows the effect of these nutrients on foliage yield, quality, nutrients uptake, and it is a good introduction with some very good visuals. As phosphorus is a most limiting mineral nutrient for plant production, much research has gone into trying to understand why there are differences in phosphorus absorption in plants and how this might be improved. Such research is reviewed in the Rammakers et al. Publication in 2010. This publication was entitled Strategies for Improving Phosphorus Acquisition Efficiency of Crop Plants, and reviewed certain techniques and mechanisms that could potentially be used in genetic engineering. The figure on the slide is from this paper and demonstrates differences between a phosphorus efficient and a phosphorus inefficient genotype, looking at root structure and how this may enable increased efficiency of phosphorus uptake. The development of transgenic plants may be used in agricultural practices. To complete your notes on scientific advances in phosphorus, I'd like you to watch the BBC video, which is an interview of Sigrid Høyer, who discovered an important step forward in our understanding of phosphorus and how we might use this in rice production. Now let us talk about the mineral phosphorus. The application of phosphorus is second to that of nitrogen in many farming institutions. There are two forms principally that are available to the plant in the soil. These are the phosphates, hydrogen phosphate and dihydrogen orthophosphate. They are collectively known as the orthophosphates. Other forms of phosphate that are available in the soil include sorbed phosphate, the mineral phosphate, calcium phosphate. This is relatively insoluble in the soil. Aluminium phosphate, again relatively insoluble in the soil. Iron phosphate, relatively insoluble in the soil. Organic phosphate slowly supplies available phosphate to plants and microorganisms. The cycling of phosphorus in your agricultural system is critical to phosphorus management. I'm going to spend a few slides here familiarizing you with this cycling process. Phosphorus is cycled as phosphate, sorbed phosphate, mineral or in organic forms. The plant can only obtain phosphorus in the phosphate form. The content common in agricultural soils. Phosphate tends to make up less than 1 mg per litre or 1 part per million of phosphate in the solution. This represents less than 1% of the total soil phosphate, i.e. it's found in very low concentrations. Organic phosphate makes up between 25 and 65% of the total phosphate in the soil. This depends on the soil type. And sorbed phosphate represents the remainder. The presence of mycorrhizal fungi, which develop a symbiotic relationship with plant roots and extend thread-like hyphae into the soil, can enhance the uptake of phosphorus, as well, especially in acidic soils where phosphorus tends to be low. The image on the slide is a simplified version of the phosphorus cycle. Phosphorus can be obtained from either weathering phosphate rocks, fertilizers, or residues from either plants or livestock. Once it enters the soil, it is then cycled in the soil depending on the form of which it is in. This cycle shows that phosphorus is converted between mineralized and non-mineralized versions of the compound. Remember, it is the mineralized version of the compound that the plant can take up from the root. You will also notice that leaching can occur in this system. It is worth noting that organic phosphorus decreases quickly with soil depth, paralleling decreases in organic matter. Phosphorus moves to the root surface through the process of diffusion. As phosphorus moves towards the root at higher rates than water is moving via transpiration. Phosphorus uptake is different for different crops and is yield dependent. It tends to range from 22 to 67 kilograms per hectare per year. There are some examples in Australia in the southern regions that have received such a high accumulated application of phosphorus that no further applications are required, and yet a sustainable optimal yield can still be obtained. Soil testing is a critical step in the management of phosphorus. In order to conduct a soil test, you should select random samples of the soil surface, that is 0 to 10 centimeters, typically between the rows and across the paddock. This is the best way to establish phosphorus status of your soil. Establish yield zones across the paddock based on yield data. Your observations will help you inform you of this in your first and second years. Phosphorus may be a cause of some of this yield variability. Adjust your phosphorus fertilizer according to your variability of your soil type and your yield zones. This will increase your profitability and allow a more sustainable approach to managing phosphorus. Different extractable methods for measuring any compound will yield different results and require a different interpretation. Typically, it is best to standardize your extraction method based on understanding your soil type and composition, pH, and what information you are after. In order to achieve this, you need to understand some of the differences between the tests. On the slide is a copy of a table I have produced summarizing some commercial soil tests for P. You can find a full copy of this on Moodle for you to download and examine in further detail. The tests that I have compared are Corwell P, Orson P, Phosphorus Buffering Index, and diffusion gradients in thin films called DGT test. Each of these tests has a different requirement or measurement, and with that an associated measured range. Sometimes this range may be in parts per million, other times it may be as a unit. The Corwell P test is based on the Corwell P test and extracts your phosphate in an alkaline 0.5 molar sodium hydrogen carbonate at pH 8.5 for 16 hours. It is different from the Orson P as the time of extraction varies. It measures the level of easily available P. If used alongside the buffering index, PBI, gives a good indication of the levels and accessibilities of P in the soil. The unit it is given in is mgs of extractable P per kilogram of dry soil. The phosphorus buffering index gives an indication of soluble P. It works on the principle that P is absorbed by clay minerals and/or precipitation in the soil, and it determines the partitioning of P between the solid and the solution phases of the soil. It is extracted in 0.01 molar calcium chloride, which contains 4 mg of potassium in the form of potassium hydrogen orthophosphate. It is typically measured in units and gives the P sorbing capacity of the soil. It can show you how much of fertilizer in a soil can be fixed into unavailable forms. The buffering capacity of a soil refers to its ability to maintain its P concentration in the solution as the plant roots absorb. The P Orson test is similar to the Corwell test. However, extraction is for 30 minutes rather than 16 hours. It does indicate a maximum plant growth and yield, but these are different amounts from the Col P as the extractable time is quite different. And finally, there has been some question of the correlation of tests such as the Col P and the Orson P in certain soil types and their ability to estimate plant yield and assess how much fertilizer should be added. The development of a DGT is a diffusion gradient test. This is where soils are moistened up to 100% water holding capacity for 24 hours. Then the P is extracted through a membrane or film. The P is measured in the film. This test can measure P values from 0 to 200 micrograms per litre and is recommended for soil types such as calcareous and acidic soils with high iron or aluminium. It measures initial soil P concentration and ability of the soil to resupply the soil P pool. It is designed to mimic plant roots. When you are considering future soil P management, it is always good to have a good historical record. Historically, the following is good to include in your records. The soil sample strategy, that is, where did you take the soils from, what depth did you select, and what spatial variation are you able to determine from your soil sampling? Do you have one sample or many from a paddock, for example? Your temporal variation, how is your P varying over time? When you're looking at this, you need to consider what crops were grown and how much fertilizer with respect to P was added each season. Ensure that you understand the soil test used and only compare like soil tests. A soil can it be defined as either responsive or non-responsive to phosphorus. Soil tests can reveal how responsive or non-responsive addition of phosphorus fertilizer will be. This will largely be dependent on the soil composition. On responsive soils, take advantage of row spacing options. For example, 12 kilograms per hectare of applied phosphorus on a row spacing of 15 to 18 centimeters may be recommended. However, you might be able to achieve the same productivity by applying 9 kilograms per hectare of phosphorus at a crop seeded at a row spacing of 25 to 30 centimeters. If you have a non-responsive soil, all row positions are acceptable for managing phosphorus. An important part of your phosphorus management is being able to calculate your crop phosphorus requirements and usage. For example, the loss of phosphorus has to be calculated in its requirements. You may see that your crop requires 10 kilograms of phosphorus per ton of plant. You may find a further loss of say 3 to 3.5 kilograms per ton and a further loss of 0.5 kilograms per ton if you were to produce straw or burn. Not only does the way you manage your crop alter your P requirements and usage, but so does the crop itself. For example, pastures are thought, if you grow pastures, it is thought best to add extra P on the establishment of your pasture, because this can improve your pasture performance. This is particularly important if you are aiming to use a low-density pasture. Cereals are thought of to require high amounts of phosphorus fertilizer, while pulses and canola require less compared to the cereals. The following table summarizes phosphorus removal. This is given in kilograms per ton of grain per hectare. The take-home message that you will note from these observations are that different plant species remove different amounts of phosphorus. For example, wheat and barley can remove between 2 and 4.5 kilograms per ton of grain per hectare, while canola can remove up to 7 kilograms per ton of grain per hectare, a big difference. Phosphorus and its application. When thinking about applying phosphorus, you should note that it has limited soil mobility. It is advisable to place in or near the seed at sowing, as this is the most effective way. However, in some crops, particularly canola, phosphorus too close to the seedling can cause toxicity issues. Top spreading of phosphorus is a very inefficient application technique and is not recommended. Phosphorus requirements are greatest during initial growth. There has been some research to show that foliar phosphorus application is a good mode of application, as it allows efficient uptake. However, there is a balance. Liquid P delivers crop requirements at a lower rate per hectare on a calcareous soil, and it can be mixed with other nutrients. But you need different infrastructure to apply liquid P versus granular P, and the cost of liquid P is much higher than that of granular P. Only on a calcareous soil or a few cropping systems where the growth and yield benefits outstrip the extra expense of the liquid P. An example of this is in the ear peninsula, where 3 kilograms per hectare of liquid phosphorus for wheat is better than 10 kilograms of phosphorus per hectare of the granular product. Therefore, the economics should be carefully considered before deciding which type of phosphorus to apply. So what should your application rate of your fertilizer actually be? Well, in order to make this decision, you must first decide if you are going to maintain your p-values or if your aim is to increase your p-values. Increasing p-values is sometimes referred to as capital applications. This is a balance between your crop growth, your yield, and the cost of the additional phosphorus. Is it worth doing this? All of these should be based on soil phosphorus test values. So, if you wish to maintain your applications, you must put enough P to cover the export of phosphorus from the paddock, in animal products, accumulation of phosphorus in animal camps, losses in runoff or water leaching to depth, any crop use of P, and note that phosphorus can accumulate in the soil because it can become tightly bound to soil particles. You should note that any loss of phosphorus through runoff is considered not ideal, as leaching can lead to undesirable environmental consequences. Usually though, in regular maintenance, only a small amount of phosphorus leads to runoff and tends to be ignored for phosphorus fertilizing budgeting purposes. An exception in this case, however, can lead to the leaching losses from sandy soils with very low phosphorus sorption capacity. If, however, you wish to undertake capital P rises, you need to replace, as per the maintenance phosphorus management, and increase the amount to raise the soil phosphorus values. Therefore, you need to understand your soil tests. If your soil PBI is equal to 80, and the aim of your raising P is to raise your Caldwell soil test by 2 mg of phosphorus per kilogram of soil once over the year, you would apply an extra 5.4 kilogram per phosphorus per hectare. In order to account for the amount of maintenance P to apply per hectare, you can use the following calculation. Kilograms of phosphorus per hectare equals phosphorus divided by the DSE times by your average stocking rate. This is an example of how to calculate phosphorus management on pastures. So why do we need to be concerned about phosphorus in the soil? Well, put simply, phosphorus is involved in many plant function requirements. And this is probably the reason it is found in such high concentrations within the plant. These functions and processes that require phosphorus include energy transfer, protein synthesis, the development of reproductive structures. It is required for crop maturity, and finally for good and healthy root growth. As phosphorus is a most limiting mineral nutrient for plant production, much research has gone into trying to understand why there are differences in phosphorus absorption in plants and how this might be improved. Such research is reviewed in the Rammakers et al. Publication in 2010. This publication was entitled Strategies for Improving Phosphorus Acquisition Efficiency of Crop Plants, and reviewed certain techniques and mechanisms that could potentially be used in genetic engineering. The figure on the slide is from this paper and demonstrates differences between a phosphorus efficient and a phosphorus inefficient genotype, looking at root structure and how this may enable increased efficiency of phosphorus uptake. The development of transgenic plants may be used in agricultural practices. So what commercial product of phosphorus should you use? Bill Manning et al. In their paper Phosphorus Fertilizers, Does Product Choice Matter? Started a dialogue with adequate phosphorus is not only an essential component of profitable and sustainable crop production, but is also an increasing component of crop gross margins. In recent years, there have been large price movements for phosphatic fertilizers, leading to interest in ways to improve phosphorus fertilizer use efficiency. There are several commercial forms of phosphorus. Originally, rock phosphorus is the raw material used in the manufacture of most commercial phosphate fertilizers on the market. During the production and processing of the rock phosphate, impurities can result. However, this is mined from a finite supply of phosphorus ore deposits. And now manufacturing has moved more towards the production of phosphoric acid. The percent of fertilizer that is water soluble has been shown to affect the yield, and this needs to be considered when selecting a commercial form of phosphorus. Phosphorus tends to be mined in the US, China and South Africa. The following depicts a generalized diagram showing the various steps used in the manufacture of phosphate fertilizers. This was obtained from the University of Minnesota, and further details on commercial production of phosphate fertilizers can be found on this website, and a link to this will be provided on Moodle. Please take note about the production of fertilizers from phosphates, such as the superphosphate of lime, which is a mixture of two salts, calcium dihydrogen phosphate and calcium sulfite dihydrate. This is produced by the reaction of sulfonic acid and water with calcium phosphate. Commercial sources of phosphorus are single superphosphates, SSP, and they contain about 8.8%, triple superphosphates, TSP, which contain about 20.7% phosphorus, MAP, which typically contains 21.9% phosphorus, and DAP, which contains 20% of phosphorus. However, you need to check from the manufacturer your exact composition of your nutrient fertilizer. I have alluded in the previous slides about the commercial production of phosphorus and how these supplies are from a finite source. Not only is it important to manage your phosphates well on your enterprise from an environmental perspective, but also because the commercial production of phosphorus may be of some concern for future generations. The following YouTube video is an outline of what is called the Phosphorus Challenge, and where these authors perceive there may be problems in future years to come. Please watch this video and take notes about why you should be more sustainable in your farming practice with respect to phosphorus. The following YouTube video is an interesting video that talks about increasing phosphorus uptake with micro essentials. Please watch this video and take notes to complete your notes on this topic. So let us summarize. In this lecture, Lecture 6 Part 3, we now understand the basic chemistry of phosphorus. We have looked in detail about how plants use phosphorus. We can list phosphorus sources, describe how you would test the soil pH to determine the phosphorus concentration in that soil and exactly what that means. We've looked at how phosphorus is made commercially and how, from a commercial adaptation, you would apply that on your agronomical crop. We've also touched on why plants need phosphorus. So that brings us to the end of Lecture 6 Part 3. You are now ready to learn about potassium, the last macronutrient we are going to explore in Lecture 6.